Hello, everybody, and welcome back. In this demonstration, we're going to talk primarily about the genetic program uh, uh, machine learning algorithm used in TSL. I've got Trading System Lab running on a problem right now, but we're going to move this aside and spend some time on some PowerPoints that I've pulled out of inventory and cover the genetic program. So why did we create Trading System Lab? Well, first off, there was a need for automated trading strategy design in the industry. It's very difficult to design manually. We have these, at that time, we had these machine learning AI algorithms out there focusing primarily on predictive modeling. We had computers that were starting to get faster, PCs that were starting to get faster with the introduction of new Intel chips, but we didn't have any way to automatically design trading strategies in a very efficient fashion. Yes, we had some code writing processes that would take and combine various functions and test them and produce reports that we could then perhaps create a trading system on. These were deterministic pseudo backtest type of processes that we wrote in a variety of languages. But there wasn't any dedicated platform that was running extremely fast that could create trading strategies on any market or any time frame very easily. So prior to 2005, I set out to create such a product. And one of my first goals was to choose the machine learning algorithm. And I had a great deal of choices that I had to go through to pick the machine learning algorithm. I asked myself before I started the project, how much longer would we manually be writing trading strategies? We've been writing trading strategies by hand since really the 70s when we first started backtesting strategies. And then in the 80s and the 90s, with the introduction of the faster chips, we were able to do a lot more work, including some work with some AI and machine learning algorithms. But we needed strong technology that could create trading strategies easily on any market. It's very efficient to manually write code. Obviously, the quant engineer needs to be enhanced with tooling. He can't manually write trading strategies forever. Started to ask myself, well, how much manpower can be saved? Can the designer really explore more? Can we enhance existing strategies that were already created in a variety of languages? Can we rediscover some new concepts or rediscover some original old concepts or discover new concepts? Can we drill deeper into the data, and does automatic design really offer a competitive edge? Well, after spending a great deal of time prototyping the project, it was very clear to me that yes, this was going to be a very important breakthrough. It was going to enhance design capability of the quant. It was going to make designing easier, faster, better, with less of a chance of overfitting the data. So again, first things first, I had to take a deeper dive into various forms of ML uh, and also look at, well, what problem am I solving here, and what area of the marketplace would this kind of technology be able to operate in? And after more prototyping, it became very clear that it could operate in almost any trading frequency, from low frequency type of models all the way up to high frequency models, depending upon your execution platform. Obviously, retail platforms can't operate in this level, and high level platforms don't spend as much time in the lower frequency because those are well covered by retail platforms. So why did I choose a genetic program over a neural network? Remember, a genetic program is different from a genetic algorithm. A genetic algorithm does not create anything new. It simply optimizes what already exists in a very fast fashion, but it doesn't create anything new. If you're using a genetic algorithm to create new, novel, and unique code structures, then you're really doing genetic programming. So if you want to do that, why not go directly to a high-speed genetic program? But I spent many years working with various forms of neural networks and noticed that they had a rather high chance of overfitting the data. They were also difficult to work with. They were slow. Pre-processing the data was a hassle, and ultimately creating the trading system out of a predictive model was full of problems. And as I've said in other demos, you can have a model that's 90% accurate in prediction and still lose money as a trading system if the 10% of time that you're wrong, you lose more money than the 90% of the time that you're correct. The equity curve then drops below zero, and you have a poor trading strategy that just so happens to be 90% accurate. So with a choice to be made, I obviously wanted something that was fast, that was accurate, that would write code, that had a low chance of overfitting, that was proven already on messy data and could be hyper-threaded and perhaps multi-instance. And many of these multi-instance and hyper-threading functions I didn't really know about when I started on this journey prior to 2005. So I chose genetic programming. It's based loosely on biological models of evolution. It simulates a path that a species goes through as it evolves, i.e., it starts off simple, it adapts to a hostile environment. Strong parents give birth to strong children, and mutations may help. And there's many books written on genetic programming. Now, there's two major types of genetic programming. There's a tree-based genetic program, and there's a register machine code-based genetic program. Well, the machine code register-based genetic program is the fastest, most efficient algorithm out there. And why use it? Well, higher level tools might be unavailable, and we're letting the machine do the work in its domain, working initially on our initial prototypes with just zeros and ones. Nothing is better from a machine standpoint than allowing the CPU to work with zeros and ones or integers or booleans. It's very fast at that level, and we needed speed. So the original preprocessors were only Boolean with Trading System Lab, and they used I believe at that time 62 variables. Now they're using 56 variables, but we have 8 outputs. So it's a multi-input, multi-output system. It's very efficient from a memory use standpoint. There's no garbage collection. So the memory consumption is very stable because it's running at the Intel assembly code instruction set level. So a little more illumination on this issue. Let's look at a big picture question. How many CPU cycles does it take to compute the following? One indicator equals y plus z. Well, CPU cycle, if we could minimize the number of CPU cycles that it takes to evaluate an expression, obviously the fitness function and the training of the model would occur very, very quickly. Well, in the case of higher level languages, it can take up to 20 clock cycles. But in the compiling genetic programming system, which is the linear automatic induction of machine code with genetic programming engine codenamed Skipolis that we use in Trading System Lab, it takes just 1 clock cycle. So Trading System Lab should be at least 20 times faster than higher level languages on a single thread. But what about hyperthreading and multi-instance? We even get a further push when talking about hyperthreading and multi-instancing. And here's the peer-reviewed white paper that goes over this calculation, and you can download this on our website under literature. So it's the efficient evolution of machine code for CISC architectures using blocks and homologous crossover. And it's written by these individuals, including our partner at RML, Frank Francone. So in genetic algorithms, we are really just adjusting pre-existing conditions. It's very slow and it's older technology. It's been around for some 35 or 40 years. In genetic algorithms, if you're using it to select rules, it's still running slow because the genetic algorithm programmed in a higher level code. In tree-based genetic programming, it's faster, it's evolving new rules, but it's still far slower than the LAIMGP, which is evolving new rules in machine code and or selecting the parameters used, and it's extremely fast because it's running at the machine code level. So a little summary of evolutionary algorithms. TSL was a post-1992 string-based genetic program. A lot of the original work on machine code genetic programming was done by RML back in the 90s and then taken to modern .NET technology, for example, by Training System Lab. So early on, genetic algorithms back in the mid 70s, mid 1970s, was designed by Holland, and that was known as genetic algorithm, and it used a fixed size bit string. Later, Koza at Stanford in the early 90s created the first really serious tree-based genetic program. Now there were other earlier versions of genetic programming, but Koza is well known for a lot of books on genetic programming that discuss the tree-based genetic program and how genetic programs can rediscover formerly patented and novel and unique solutions in a variety of industries. So in the evolutionary trader design, we know that traders must trade profitably or they're deleted. They're simply returned to memory. Profitable traders compete with other profitable traders, and profitable traders are allowed to reproduce. Some will be subject to random mutations, and there will be reproduction that will be subject to crossover. And traders will be tested out of sample continuously during the design. And that's a very important feature of Trading System Lab, to be able to show you the out of sample performance during design. So you don't need to wait until you're done with the design to test on blind data, on out of sample data. Another interesting thing we saw about this type of machine learning, where we're connecting a trading simulator to a genetic program, is that even though you may not be focusing directly at a metric of a trading system, that metric can improve just simply by improving the net profit, for example. So in Trading System Lab, we invert a metric of a trading system, and that becomes an error function. We use that error function in Trading System Lab, so we're creating a minimization of the error function. So after a few generations, we have a equity curve that looks like this, but if we let it design even more, the equity curve straightens out. Drawdown, which was not part of the fitness expression, is reduced, even though it was not directly a part of fitness. So that's a feature of this. So if I wanted to design a trading system with low drawdown, I may not have to have drawdown directly in the fitness equation. I can design a trading strategy with very low drawdown by using other metrics in the fitness expression. And this fitness expression can be complex. In fact, in Trading System Lab, we have a FFAPI DLL that you can write in C code and link to the TSL engine, and it will use that fitness function. For example, you may want to start by designing a million strategies using net profit over drawdown as your fitness expression. And then after the first million strategies, you may want to then focus only on net profit or other combinations of fitness objectives. Here's an example of a fitness function that could certainly be used in Trading System Lab, the adverse maximum retracement fitness. Um, so there's really no limit to the type of fitness expressions that you can have in Trading System Lab. And in TSL, as we know, if you've been watching earlier demos, we have 41 fitness functions, including the FFAPI DLL fitness function number 41. So we have fitness functions like Sharpe ratio and straight net profit over the square root of the standard deviation of return. And if you don't know which fitness function to use, well, we have a program called EvoRun, which will let you iterate through each one of these fitness functions and present you with a grid that you can then do a grid search and evaluate what are the top fitness functions for your market under study. Okay, so to use a machine to completely design the trading strategy, we need to invert this process. And we start with an objective function like Sharpe ratio. We invert it. That gives an error function. We set that error to the machine learning sim engine. We start the process. We allow re-randomization multi-run to occur. So the genetic program simulation routine is stopped and started multiple times. In this run that I currently have going, it has started and stopped 29 times already. So about once every 30 seconds or so, it has started, it has stopped and started. Now, what happens when it restarts? Well, the genetic material under randomized parameters gets re-randomized. The population size gets re-randomized, the usage of parsimony pressure, as well as the mutation rate, crossover rate, and homologous crossover rate. Now, where can we see that while the engine is running? We can see that here in the monitor project pane on the right side of the screen. So in the current run, we're using this population size, this max program size, this crossover rate, homologous crossover rate, and mutation rate. And at the next run update, all of these numbers will become re-randomized again. This helps us crawl up a global optimum as opposed to a local optimum. So we allow convergence to occur, testing out of sample in design time. So as we know, we're testing out of sample here, and we're observing a run log of how out of sample is improving or decaying during the run as a run log. Now I'm refreshing these run logs from 0 on every run just to make the GUI more active in this case. So we apply parsimony pressure. What does parsimony pressure do? Well, parsimony pressure reduces the size of a program down to its smallest possible number of variables. So parsimony pressure will look at several different solutions. If they're both approximately of the same performance or the same fitness, then it will choose the simpler trading strategy to allow to continue in the evolutionary process. So we'll discard the more complex solution in favor of the simpler solution. This is Occam's razor. We want a simple trading strategy to emerge. And we rotate the terminal set, trading tactics, and fitness functions. So we can do that using EvoRun or DAS. And then we export code automatically. So I've been talking about expectation a lot, and it's important because we need to solve the expectation equation to know how well our trading system is doing. And here's the basic representation of the expectation equation. The expected value or the average trade of the trading system, in other words, net profit divided by number of trades, equals the probability of a win times the amount won minus the probability of a loss times the amount lost. It's really one equation and three unknowns, since the probability of a win is 1 minus the probability of a loss. This equation is still unsolvable, or it's solvable with an infinite number of solutions, all lying under the theoretically perfect trading system. So if we plot the theoretically perfect trading system, it's lying way up here in the results, and what we're witnessing are equity curves that lie under that theoretically perfect trading system. It's all because of the unsolvability of the expectation equation. We needed to solve this equation. We needed to connect the trading simulator to the learning machine and have it go through many millions of trading strategies. So why not just try to predict the market? Well, we've talked about this. If you try to just predict the market, you still don't know what the expectation is. So there's a lot of learning algorithms out there, and I spent a lot of time looking at many of these. Um, some of them work okay in predictive modeling. There are algorithms of algorithms that focus on predictive modeling, and I spent a solid year with just one of them, studying it, only to discover that it was not appropriate for the type of work that we're doing. So I focused my attention in this area here, the grammatical evolution, genetic algorithm, genetic programming group of algorithms, and chose the RML LAIMGP because it's fast, accurate, and it writes code. Many of these others are just way too slow to really produce code, or they require a supercomputer that only a very few people have. So it's really not appropriate for a package that's going to be distributed to traders worldwide at a reasonable cost. So in the prediction approach, we start with data and a model. Then we predict, and then we have to show expectation. And if it's not good enough, then we refine everything. And if we're happy with it, then we implement it. Most of the time, it's not good enough. So this is very inefficient way to do this type of work. Why not eliminate the prediction model, the prediction block, eliminate the prediction block altogether and connect the model directly with the trading simulator and the data. Let it all play together in its own way, trying to improve upon what we all know of is a trading system. And if we're happy with it, then we implement it. That's exactly what's happening in Trading System Lab. It's getting better at trading as it's trading in the simulator. Ultimately, we will stop the run and export the code and implement it. So a trading simulator and system, if you will, maps data to equity curves. So here's our theoretically perfect trading system, and here's all those trading strategies that lie under theoretical, like the ones that we're designing now. So we can calculate the equity stream as a function of time and use that type of mathematics within the trading simulator as the connected engine to the machine learning environment. So looking at the architecture another way, we have very fast code. The fastest code is down in the GP engine and the simulation routine. That's really where we focus on making the loops run as fast as possible. We also want fast loops, but they don't have to be the absolute fastest in displaying the out of sample or displaying the full data or even computing the basic fitness of the routine. That can be a little bit slower. At the more slow level, pre-processing, which is done before the design, that can be a lot slower because it's only done once. In the basic way to use Trading System Lab, it's only done once, and it doesn't need to be done very fast. Same thing with translators. So I wrote the translators in C#. The GUI is .NET, and that just needs to update at .NET rates. So it also doesn't need to be run at the very fast level, just fast enough to display the information to us in an easy to read way. Ultimately, code is produced. That code is stuck between the market data and the execution system, and away we go. We have machine designed a trading strategy and implemented it. So in TSL genetic programming type of learning, it's considered supervised learning, although there's no supervisory signal. We do not have a target variable in our preprocessor. I'll show you an example of the preprocessed data set here. So it's in the TSL data file, and I'll pull up an example of that data now. Okay, so here is strictly the Boolean data for preprocessor number one. It's a Boolean set of information, just zeros and ones. In the far right columns, this is row by row data, we have the theoretically perfect trading system, the date, open, high, low, close, and a timestamp. So these are all integered variables, and integer runs the fastest. So each one of these rows of data represent 56 inputs and market data. No predictive column at all. We do not have a predictive column. This column of data might be answering the question, is the current bar's close underneath or above a moving average, for example. Another column might be, is this bar a two-bar pattern, a, um, a constricting range? Whatever it is, it's there in a column and it's available for use in TSL as the preprocessed data. The population is initialized. Trading strategies are initialized with random signals. So we don't have any predefined existing trading strategy. When you start the run in Trading System Lab, it's a blank sheet of paper. The tournament is run within the population applied to the trading strategy, and that tournament goes through. Within that tournament, mutation, crossover, and reproduction happens. DEMS enhance geographical diversity by interacting with regions that are also representative of the solutions available in the universe of solutions in the population that's available. Parsimony pressure favors simple solutions, and then after n GWI occurs, the run restarts. Where is GWI? It's under setup learning options right here. I have it set at 1 because I want my GUI to update many times a minute, and for the purposes of this demo. Normally we run that at a higher level, like 3 or 5 or some higher number GWI. So after GWI occurs, the run is reinitialized and starts all over again. New trading algorithms emerge and improve based on the error function that we've discussed. Algorithms learn to trade better as they trade in the simulator. And after X runs or user termination, all runs stop. Right now, I have stop criteria set at 10,000. I'm never going to get that high, but that's where the run would stop if I let it run that long. But I'm going to terminate it long before that. Finally, code's exported, translated, and ported to an OMS EMS. So run randomization occurs here in setup learning. This is where we adjust all of these criteria. If we don't want to randomize the population size, for some reason, we deselect population size. The genetic programming parameters are set here under single run learning setup, under single run setup learning options, single run parameters, and here. This is where parsimony pressure is set. This is where the genetic program is configured. This is the starting population size, by the way. Here's where you can enable or disable DEMS. DSS is not used. This is not a predictive model, so we're not using DSS. The maximum program size is here. Typically, we like to keep this nice and small, so the trading strategies that emerge are very, very simple. Normally, you wouldn't go higher than 80 over 256. Let's see. On the program size, on the Search operators here. We have the block mutation rate and the mutation rate here. These are the initial mutation rates set for the genetic program. And we like running these numbers right here. A lot of homologous crossover. A lot of homologous crossover seems to help the design. In the instruction sets, if we're going to adjust anything deep in the genetic program, this is one area that we might consider adjusting. The the two areas of data transfer and rotate stack are used are increased in value if we want to have the genetic program be able to discover more readily the higher level GP outputs. Now, where would I use the higher level GP outputs? Well, one of the places is the GP stops and GP exits. So these make use of the higher level GP criteria, and you may want to increase those instruction sets to let the genetic program find these better. This is covered in the user manual, but we also use the higher level GP parameters to evolve money management, for example. So again, that's another one that uses additional GP outputs. By the way, do you see what I'm doing with the mouse? I'm hovering the mouse over various text here, and this will tell you what um, what is important about the particular setting that we're hovering the mouse over. It's probably more enhanced in the initial configuration screen. So if you have a question about a particular setting, just hover your mouse over it and read what the tooltip is. There's a lot of great information in these tooltips. Okay, so we've covered most of the GP settings and the instruction sets. The TradeStation functions for translation into TradeStation are shown here. These allow C code, these allow easy language to be like C code. When we stop the run in Trading System Lab, we will be converting machine code into C code. Then we will be converting that C code into easy language code. Well, in C code, you can divide by 0. That's called an INF, or infinity, an infinite number. But in easy language code, the program would crash. So we need to program around that, and we did that by creating a group of functions. Now, if you notice here, I've got a CEL divide function and a divide alternate 1. Dividing by 0 is the issue, and these functions allow divide by 0. But there's an alternate way that may come up occasionally um, in the division aspect. The way to think about this is in Trading System Lab, when you go to options and then single run parameters and then the instruction sets, you'll see here under division that there are 4 different ways to divide in assembly code. Now in algebra, there's only one way to divide, right? A over B. But in assembly code, there's 4 ways to do the division. And here are the assembly code instructions for that. Well, when you go to translate the code from machine code to C code, it may invoke a different divide architecture. We needed to take that into account in the easy language, and we did so in this divide alternate. So this is covered in the user guide, but if for some reason you do not get a translation that occurs correctly, there's a way to simply quickly change the easy language function from divide to divide alternate 1, and that may in fact solve the translation problem that you would be having with that code. Obviously, we're here to help you if that becomes an issue. Most clients don't have very many issues with translation, but in our testing before we released the product, we tested thousands of various combinations of trading strategies and found these small little corner cases, I like to call them, these small nuances of machine code learning. So in evolutionary-based computing, induction of machine code, there was an old way to do this kind of machine code evaluation, and there's the new way, and this is the way that Discipulus, that RML does it. It's direct execution upon the machine code. There's no intermediate steps at all involved. It's directly executable on the machine code instructions. And here's the peer-reviewed white paper that's downloadable on our website that explains this in more detail. It's also covered in, I believe it's also covered in the genetic programming book. A very important aspect of this kind of machine learning is what we call non-homologous crossover. In homologous crossover, the size of the string of the children will be the same size as the parents. So in this case, there's 4 blocks. The children would be 4 blocks long. But in non-homologous crossover, the trading system can vary its size during evolution. So we can combine parents of the same block size, and that will give rise to children of varying block size. This is exactly what you want in trading strategy design. I don't want to have to be restricted to a particular size. I want the trading strategy to be able to grow and shrink as it's evolving, as it's discovering how to consume the data and design the best trading strategy. So this is very unique in Trading System Labs genetic program, this non-homologous crossover. You won't find this in other algorithms. I've talked about the function sets. You need to tell the computer that it can add. So you have to have these instruction sets. If for some reason you wanted to turn off addition, you would simply deselect the addition function here. And as an experiment, you could certainly try to design a trading strategy using only multiplication, addition, subtraction, and division if you wanted to. So in summary, the genetic program that we use in Trading System Lab is extremely powerful. It's been proven in industry tests. This was a test conducted quite a long while ago by RML on a government project that they were working on to try to find unexploded buried bombs. That's what a UXO is. And they competed against many other companies like Battelle and Applied Physics, NAVIA, Naval Research Lab, and ESCO. And this chart shows where those companies' results laid, applying their best technology to this. Being higher above this diagonal is better, being lower is worse. Well, here's Discipulus, way out here. It outperformed all of these people. And that's very messy data trying to find signal in this kind of deep underground imaging data. It's very messy data. Well, that's what we want. We work with messy data in the financial sector. It's non-stationary, very messy, noisy data. So I want an algorithm that that works very well on this data. So I hope with this demonstration that you now have a better understanding for what's behind the genetic program. When you click on Setup Learning and configure these parameters, one final point, when you configure these parameters, make sure that you save them up here, either File Save or click the disk. The genetic program parameters are saved here when you configure them here. The simulator is adjusted here in DAS or here in simulator setup, and those parameters here are saved using these buttons here. Save settings, quick save settings, etc. On DAS, you have a setting button here to save the settings and then load the settings, which will save you time in reconfiguring these GUI. So after you've configured the GUI, press Quick Save Setting, and the next time you come into the GUI, just hit Quick Load Settings, and the settings will be loaded. When you're here in the genetic program and you save the settings, what you've done is you've updated the .bsts that are held in the TSL project folder. So these .bsts are where the genetic program parameters are saved. Only the genetic program parameters. That's not where the simulator is saved. The simulator data we can see is saved right here in the appconfigure.txt, and that's a text readable file. Many of the files in Trading System Lab in the data folder are text readable. So they're they're um, they're shown in the GUI of Trading System Lab, but they're also text readable by any text editor that you want to use. Just click on the uh, on the text file, and here it is. Here's the data info file. Very simple data info file. Um, and there's lots of other text readable files in the TSL data folder. Well, we hope you enjoyed this demo. Thank you very much.